Hello and welcome to NASA's Jet Propulsion Laboratory in Pasadena, California. And our special preview of Cassini's grand finale. You know, in just a couple of weeks, NASA's Cassini mission to Saturn will begin the final chapter in its remarkable story of exploration. And we're here to brief you on what it's planned to do and what we hope to learn from it. Our speakers today: joining us from NASA headquarters, the director of NASA's Planetary Science Division, Dr. Jim Green. Back here at JPL, the Cassini program manager, Dr. Earl Mays. To his right, Cassini project scientist, Dr. Linda Spilker. And finally, Cassini guidance and control engineer, Joan Stupik. Now, a reminder to reporters dialed in on the phones, please dial *1 if you have a question. And members of the public as well as the media can ask questions on social media via Twitter using the hashtag AskNASA. And with that, we'll throw to Washington for comments from Dr. Green. Jim?
Thank you very much. You know, in 1610, Galileo, with his very primitive telescope, observed Saturn for the very first time. And he was quite astounded with that beautiful object. It looked very different than any other object he had seen through his telescope before. It had these wings that sort of stuck out. He continued to observe it for many years, making many detailed notes in his notebook. This caused quite a flurry of interest from other astronomers building better telescopes over many decades after that. And in 1676, Giovanni Cassini observed the rings and saw a division between ring A and ring B. And that division we call now Cassini's division. Fast forward to modern times, and in the 70s, we launched Voyager 1 and Voyager 2. And in the early 80s, as they flew through the Saturn environment, giving us spectacular views of the moons and the rings and the planet itself, we knew we had to get back there. Well, it took quite a while, actually, to formulate a new mission, and the right mission actually got together in the form of a Cassini. We then called Cassini, named after Giovanni Cassini from the Cassini division, and the Huygens probe, another fabulous scientist from Europe who had been also observing with his telescope. That spacecraft launched in 1997, finally made it to the Saturnian system in 2004. It immediately went to work. We dropped the Huygens probe off onto a fabulous moon called Titan. Now, Titan, with a huge atmosphere, is much bigger than even the planet Mercury. It settled through the atmosphere, landing down on the surface, making spectacular measurements of the temperature, the density, and the composition of the atmosphere. Cassini continued to make other observations of Titan, telling us a lot about the liquid that's on its surface. It's not water, it's methane. Titan, which seems so familiar to us because it has liquid, it has a cycle of evaporation, transport, and then rain and runoff that creates new bodies of water, but it's a completely different world and a very fascinating one. Cassini kept going on, making other fabulous discoveries. Another moon called Enceladus, which just sits outside the rings of Saturn, has huge sheets of water ice pouring out of cracks in the southern hemisphere. A small percentage of that actually escapes the moon and forms a ring called the E ring that's outside the A ring of Saturn. Cassini also made fabulous measurements of the planet Saturn itself, observing spectacular storms, lightning, beautiful cloud formations, and many other new discoveries that it continues to make in that system. But now we're coming to the end. As it runs out of fuel, the things that it can do are quite limited. At least we thought, until we decided on a new approach, a grand adventure, new discoveries that we can use this system to make. And we call that the grand finale. And here is a little video that we've put together that I hope you'll like, that gives you a little overview of what to expect.
A lone explorer on a mission to reveal the grandeur of Saturn, its rings and moons. After 20 years in space, NASA's Cassini spacecraft is running out of fuel. And so, to protect moons of Saturn that could have conditions suitable for life, a spectacular end has been planned for this long-lived traveler from Earth.
5, 4, 3, 2, 1. And liftoff of the Cassini spacecraft on a million-mile trek to Saturn. We have cleared the tower. Its program is in. Its program is in.
In 2004, following a 7-year journey through the solar system, Cassini arrived at Saturn.
To the SOI burn attitude or pointing position, and light up the rockets.
The spacecraft carried a passenger, the European Huygens probe, the first human-made object to land on a world in the distant outer solar system. For over a decade, Cassini has shared the wonders of Saturn and its family of icy moons, taking us to astounding worlds where methane rivers run to a methane sea, where jets of ice and gas are blasting material into space from a liquid water ocean that might harbor the ingredients for life. And Saturn, a giant world ruled by raging storms and delicate harmonies of gravity. Now, Cassini has one last daring assignment. Cassini's grand finale is a brand new adventure. 22 dives through the space between Saturn and its rings. As it repeatedly braves this unexplored region, Cassini seeks new insights about the origins of the rings and the nature of the planet's interior, closer to Saturn than ever before. On the final orbit, Cassini will plunge into Saturn, fighting to keep its antenna pointed at Earth as it transmits its farewell. In the skies of Saturn, the journey ends, as Cassini becomes part of the planet itself.
What a spectacular end to a spectacular mission. You know, I feel a little sad in many ways that Cassini's discoveries will end, but I'm also quite optimistic that we're going to discover some new and really exciting science as we probe the region we've never probed before. It can be kind of risky. You know, the ring material actually falls into Saturn, and it doesn't take much to stop our spacecraft at the velocities it's flying. But for more details on how this will occur and what our plans are, let me turn it over now to the project manager, Earl Mays. Earl?
Thank you, Jim. That video is a very hard act for us to follow. We get goosebumps and a little emotional every time we see it. But let me try. Thank you all very much for your interest in the Cassini mission. I wanted to augment Jim's comments with just a couple more of my own. One is just to acknowledge again the tremendous international effort that the Cassini-Huygens has been. We had 19 nations and 3 space agencies contributing hardware to this Cassini-Huygens mission. We have remote sites all over the world. It's truly an international triumph. And again, I want to also acknowledge not only the tremendous scientific discovery that has occurred, but the engineering achievements, the absolutely brilliant, creative, and innovative mission design, the astonishingly accurate navigation, the flawless engineering, and the meticulous melding together of 12 disparate scientific investigations into a cohesive whole that has essentially rewritten the books on Saturn. It is just a phenomenal achievement. Cassini's legacy is absolutely assured. We are in the books, guys. It is just there. But the best is still yet to come, perhaps, but we are certainly going to provide more excitement. Let's bring back one of those clips, please. We are going to dive into the gap between the rings of Saturn and Saturn's atmosphere, a place no spacecraft's ever gone. We're going to be going 70,000 miles per hour into a 1,200-mile wide gap. At that velocity, oh, by the way, we're going to be doing it from 1 billion kilometers away. It's all being run from right here. Just another stunt. Even a piece of sand at that velocity will take out one of our instruments, or if it's in the wrong place, could cripple the spacecraft. So this is something we wouldn't want to really try any other time. But now it is the time. There is a question I suppose we've been asked many times is, why are you doing this? You've got a discovery machine that's performing flawlessly. What's going on? Well, the short answer, and Jim alluded to it, is we're out of propellant. Back in 2010, we decided then that we would use every last kilogram of our propellant to explore the Saturn system as thoroughly as we could, end up with no gas in the tank, but at the same time had a very serious constraint. Cassini's own discoveries were its demise. Enceladus has got a warm, saltwater undersea ocean, and it's got plumes coming out. We cannot risk an inadvertent contact with that pristine body. Cassini has got to be put safely away. And since we wanted to stay at Saturn, the only choice was to destroy it in some controlled fashion. And that's when the grand finale came in. The mission designers again conceived and found a way for us to go between the gaps. And that's right where we're going to go, starting April 26th. In about 3 weeks, our final Titan flyby will push us into that gap. So maybe we could go to the next slide for just a sec. I'll speak to a little bit. This ball of yarn is what we call it. If you step back a little bit, you'll see a bright spot in the middle. That's Saturn. Those are all of the grand solstice mission orbits. And you can see it's gone all over the system. Every time that orbit bends, kinks, changes, it's Titan. That Titan flyby is moving us all over the place, and we've exploited it to perfection all over the Saturnian system. But now, the color ones, the kind of goldish-looking ones that you're looking at, are where we are right now. A Titan float has put us in there, and then one more Titan flyby. And let's jump again. I'll speak quickly. You're going to see this again in a second. But one more Titan flyby is going to put us into that gap between Saturn and its rings. And you can see the orbit of Titan there. And what's even funnier is that as we go by, Titan's still messing with us. And so once again, it's going to come by and it's keep pushing the spacecraft in and out. And I'll show you a little bit. But this one, that last kiss goodbye, will put Cassini into Saturn. This is a roller coaster ride. We're going in and we are not coming out. It's a one-way trip. Let me go to the next slide for just a sec. This is not without risk. That is a high contrast view of the inner rings of Saturn. And so you can see the dust kind of extending and slowly disappearing into the black. Now, if we go one more click, you'll see where we're going to fly. That's the plan. We're going to stay as far away from the visible dust as we can, and we're using our very best models of the rings that we've been developing. I mean, we have some of the best ring experts in the world. Our very best models to extrapolate into the region we can't see in order to determine if we can be safe. So again, let's go one more slide. There are the 22 proximal orbits, and here is what it looks like from a Cassini point of view coming in. Starting left to right, each of those final orbits, and as you can see, that red one on the end is the last one. Now we go in a little bit more. We'll have the artist put in where we think we're going to be. Again, from the navigational precision, this is an easy shot. Our problem or concern, I should say, is not our accuracy, but have we modeled that system correctly? And so for a couple of those orbits, you see that the ring plane crossing is kind of flirting with the edge of where we think it's safe. Well, that's where this comes in. This is a model of the Cassini spacecraft, and this right up here is our high-gain antenna, a great big dish. And if you notice, almost all of the instruments, if you point it the right way, are shadowed or shielded by that antenna. So first time in, we're going to go behind the high-gain antenna, having it shield everything we possibly can. Of course, the magnetometer's hanging out here, and they're on their own. But everybody else, everybody else will be back behind the shield. And what we'll do is we have a couple of instruments that can tell us very quickly if we've modeled the dust correctly. If we have, great. We're going to use the high-gain antenna a couple more times. You can see a few of those revs where we sneak up over the dotted line, and we will shield ourselves again. But every time else, we'll turn the spacecraft over to one of or several prime instruments to interrogate an unexplored region of Saturn. If we get surprised, well, we've got a bunch of contingency plans. We'll do some broken field running. We'll milk the very best out of this. And if we really get surprised, if indeed we've modeled so badly that there are BB-sized material out there, well, Cassini will still finish up exactly where we've planned, but we may end up with a little bit less science than we had hoped for. But we've got every confidence that our models are correct and that we are going to finish this up exactly as we say, with a grand finale and a spectacular ending. On a more personal note, there are a couple of different perspectives on this. One is just excitement. We've been flying the spacecraft for 20 years. Some of us have been here on the mission the entire time. I can't say that I'm one, but it's been a lifetime or a career of just achievement. And every time we come around, we find more ways to repurpose the spacecraft, to use it more creatively, and to find more and more revelations. I'm excited about that. We saw something 2 weeks ago that we've never seen before. I fully expect that to continue for the next, well, I've lost track, probably 5 months. It's going to be phenomenal. A tremendous sense of pride. This mission, and anyone that's been associated with it, should just hold their heads up because it has just rewritten the books. And again, it just is going to continue. This book, this spacecraft, this mission, the folks that are on it, it's just been phenomenal. And of course, there's the sense of loss. We, humankind, through us, have been at Saturn for 13 years. You can get up in the morning, you can get a weather report, you can see what the images look like, you can get the status on the space weather, magnetic fields. We are connected, and we've connected the entire planet. The social media and everyone else is all on this ride with us. That's going to go away, and there's unfortunately not a substitute for that for some time to come. We've had an incredible family. It really takes a village to fly this thing. Only this village is all over the world, and we're connected with high-speed data lines rather than backyard fences. But it's still exactly the team, the family that we've developed, the personal relationships. It's going to be a hard thing to let go of, and I'm hoping to see many of you and many of us in other places. It's been a ride of a lifetime, and I would not trade it for anything. And with that, I'll turn this over to Linda Spelter.
I'm the Cassini project scientist, and as the project scientist, I lead a team of 300 scientists from all over the world. And our goal is to use this capable spacecraft to collect the best science that we can. Now, I've worked on the Cassini mission for almost 3 decades. My oldest daughter, Jennifer, started kindergarten when I started working on Cassini, and now she's married and has a daughter of her own. Those decades of Cassini have flown by, and now here we stand on the brink of the grand finale. In so many ways, the grand finale is like a brand new mission. We're going to a place and obtaining data with the Cassini spacecraft we could only obtain in doing it this way. In fact, I wouldn't be a bit surprised if some of the discoveries we make with Cassini might be the very best of the mission from these grand finale orbits. Now, I'd like to share with you some of the highlights in particular about Saturn's rings and about the planet itself. And if I could have the first graphic, please. This is a view of Saturn's rings. Now, this system is huge. If you take Saturn plus its rings, it would just fit in between the Earth and the Moon, a tremendously huge system. And one of the things we can do with the rings is, in the grand finale orbits, for the first time, address the question of the origin and the age of the rings. We'll do this by measuring the mass of the rings very accurately. If the rings are a lot more massive than we expect, perhaps they're old as Saturn itself. And they've been massive enough to survive the micrometeoroid bombardment and erosion and leave us with the rings we see today. Now, on the other hand, if the rings are less massive, perhaps they're very young, maybe forming as little as 100 million years ago. Maybe a comet or a moon got too close, got torn apart by Saturn's gravity, and we have the rings that we see today. The other thing we can do for the first time is determine the composition of the ring particles. Now, we know that Saturn's rings are 99% water ice, but we're not certain about that other 1% non-icy constituent. What is it made of? Could it be tiny grains of iron, silicates, organics, a mix of all three, something else we haven't even thought of? When our cosmic dust analyzer goes through the ring plane, we'll scoop up ring particles and directly taste and measure the composition of those particles. And then imagine the pictures we're going to get back of Saturn's rings, in particular the C ring and the D ring. Maybe we'll even see one of those largest ring particles as we go by. Wouldn't that be very cool to do as well? If we go on to the next graphic, then we have the planet itself. Basically, as we're skimming close to the planet, we'll have the best views ever of the poles of the planet. We'll see the giant hurricanes at the North and South poles. We'll also see, this is the North Pole of Saturn, we'll see the giant hexagon, six-sided jet stream that's 2 Earth diameters across. What keeps those 6 sides in place? It's been there for decades itself. Perhaps getting close with Cassini, we can answer the question, what keeps the hexagon there in this particular shape? We'll get to see the clouds up close, maybe little tiny storms, little vortices whirling around. Some of the best images ever of the planet itself. And then, of course, on the last 5 orbits, we're actually going to dip our toe in the atmosphere of Saturn. With our ion and neutron mass spectrometer, measure the composition of the atmosphere. Now, it's mostly hydrogen and helium, but what else is there? And in what abundance? And of course, on our final orbit, we're going to actually point the instrument in the direction of the atmosphere coming from Saturn and make measurements until the very final moment when Cassini turns away and the mission ends, going as deeply as we can into Saturn's atmosphere. Now, if we go on to the next, we're also going to look at the aurora of the planet as well. This is in the near infrared. It's a false color. You can see the greenish aurora at the South Pole, the similar aurora at the North Pole, so the northern and southern lights of Saturn itself. And if we go on to the next graphic, we're also going to get an incredible view of the interior of the planet with our gravity and magnetic field measurements. With our gravity measurements, we'll measure the size of the rocky core on Saturn. That's right in the center of the planet. Is it 1 Earth diameter in size, 2 Earths, smaller? We'll find out for the first time. We'll actually be peeling back the atmosphere and looking inside the planet. Now, any irregularities in the gravity field will tell us how deeply those winds continue to blow on Saturn. Are they shallow winds, maybe only going down 150 miles or so? Are they deep winds going 10 times as deep in the planet, or deeper still? We'll be able to make those kinds of measurements. And then with the magnetic field, we'll be able to get, for the first time, we hope, the length of a day for the interior of Saturn. How fast is Saturn rotating? If there's just a slight tilt of the magnetic field, it will wobble around and give us the length of a day. And then the magnetic field will help us understand the interior. We can see in that gold region in the outer part of Saturn, that's the molecular hydrogen. That gray boundary is where you go to the metallic phase as the pressures increase inside Saturn. In the metallic phase, currents can flow, and you can see the blue magnetic field lines coming out from the interior of Saturn. Now you can see the rings are really good at shielding the magnetic field lines, but you see field lines outside the rings and in that region where Cassini will fly, and we'll look at the radiation belts in that particular region as well. So the grand finale mission is absolutely incredible, flying in a region that no spacecraft has flown before. And getting this close to the rings and the planet, that's a once-in-a-lifetime experience for a scientist like me. We've wanted to do this for a long time, and we had to wait for just the right time and just the right mission design to actually fly in this particular region. And I can't wait for those new discoveries in the grand finale mission, and I'm just incredibly proud to have been part of the Cassini mission from the beginning until the end. But of course, it's really going to be hard to say goodbye. To say goodbye to this plucky, capable little spacecraft that has returned all of this great science. And then to say goodbye to the Cassini family. We've been together for a long time, and we've flown this spacecraft together. So on that final day, it'll be a very sad time and hard to say goodbye. And with that, I'd like to turn it over to Joni Stupic. She's the guidance and control engineer for Cassini.
Thanks, Linda. So I am part of the team of engineers that manage and control the spacecraft itself. And specifically, I work on the orientation of the spacecraft and point the cameras. Now, all of the spacecraft movements that we've designed for the whole mission through the grand finale are now available for anyone to check out in a program called Eyes on the Solar System, which you can find at eyes.nasa.gov. Now, Eyes on the Solar System is a free interactive software that allows anyone to explore various spacecraft, not just Cassini, and planets in our solar system. Now, the special Cassini module highlights the grand finale specifically. So to enter the Cassini module, we'll click right here. Now, the first thing we can do is check out and see where Cassini is right now. So at this very moment, this is Cassini's position and orientation relative to Saturn and also relative to the rest of the solar system, which is hanging out right there. Now, to enter the grand finale module, I hit this button. And here we have a zoomed out view of Cassini's orbit right now. Now, when we come in close to the rings, we will still be outside the rings. So to make that final hop from outside the rings to inside the rings, we need Titan's help. So our very last Titan flyby will be on April 22nd. And this is a simulation of what the spacecraft will really be doing on that day. These purple lines here represent the radar beam as it sweeps across the moon and takes science. Now, all of the spacecraft movements shown in the simulation are using the real engineering data that I use every day to do my job. Now, when we get a zoomed out view of the trajectory, we'll see what Titan has done to our orbit. We can see that that last big tug that Titan gave us has kinked our orbit right here. And so it's now popped us onto the very first of the grand finale orbits. So the next time that we come in close to Saturn, we'll be inside the rings. So the first time that we'll plunge through that gap will be on April 26th. And you can see here we're coming in from above, looking at a bunch of things like the hexagon and taking new science. And as Earl talked about, the very first time that we plunge through the gap, we're going to be at a very specific orientation. Now, as Earl was talking about, we just don't know exactly where that D ring comes. We think we know, we're pretty sure, but to be on the safe side, we want to protect all of the science instruments on the body of the spacecraft from those pieces of dust going. You can see here, right now at 74,000, it gets up to 76,000 miles an hour. So at those speeds, even a tiny piece could do damage to our science instruments. So we use our high gain antenna as a shield to protect the rest of the spacecraft. And the other thing that we can see is our distance relative to the cloud tops of Saturn. So in this case, we can watch as we plunge through, and the distance gets down to about 1,800 miles, which is very roughly the distance across the continental United States. And in space terms, that's a really short distance. And we can also sort of get a little peek through eyes on the solar system at some of the spectacular views that we expect Cassini to see. But that was just the first of 22 proximal, we call them proximal orbits because we get in close proximity to Saturn. And so we'll do a total of 22, and so we'll be crossing through the ring plane about once a week. And as Earl alluded to, each time we come out far away from Saturn, Titan is pulling us a little bit, and that essentially moves where we intersect the ring plane around, and so we are different distances from Saturn each time. And so you can see that in Eyes on the Solar System, we have the real trajectory, so you can see each time how far away we'll be from Saturn. And the very last time that Cassini comes to cross the ring plane, we will enter into Saturn's atmosphere and not come out the other side. And we can see right here, this is the point that Cassini will be intersecting with Saturn's atmosphere. And that will be a very emotional day for all of us. So Cassini received federal funding in 1989, and I was born in 1989. So you could say we're the same age, born in the same year. And Cassini left Earth when I was 8 years old. And so it's been an incredible honor and privilege for me to begin my career working on the last 4 years of such an incredibly successful mission. So I'm going to turn it back to Earl, and he's going to talk about the last few minutes of Cassini's life.
So that's how we plan to end one of the most amazing voyages of exploration. If I could have the next animation. Cassini will enter Saturn's atmosphere on Rev 22.5, valiantly fighting against the ever-increasing torques from the atmosphere, pointing its high-gain antenna to Earth to send down every last precious bit. We will be sampling the atmosphere of Saturn. Every bit will be transferred back as quickly as we can. Inevitably, Cassini's going to lose the battle. It has got small thrusters. It wasn't built for the atmosphere, and eventually it will lose point and control. Shortly after that, it will fall apart, break apart. It will melt. It will vaporize, and it will become a part of the very planet it left Earth 20 years ago to explore. The spectacular ending, the grand finale, going out in a blaze of glory, is a phenomenal conclusion to a chapter in humankind's exploration of the planets. Just a chapter. The book is not complete. There's more to come. But this has been a marvelous ride. Thank you.
All right, thanks so much to our speakers. We have time for questions now. A reminder to reporters who've dialed in, please dial *1 if you have a question to ask. We'll start here in the audience at JPL. Please raise your hand if you have a question. And I see a couple down here. Why don't we start close to the aisle and then go inward. Please wait for the mic and state your name and affiliation.
Hi there, Ian O'Neill for Space.com. Congratulations on a fantastic mission. I've been captivated ever since I started science communication, so it's been an amazing voyage. I just had a quick question on what you think Cassini will encounter as it goes through the gap. Have you done statistical analysis that it could get hit? I mean, is there like a percentage chance that it will just be lost? And if it is lost, is there going to be any contamination issues, or is it all just going to eventually fall into the planet anyway?
I think that one's mine. Yeah. We've done a lot of modeling, and what we believe we've gone through the rings, other diaphanous rings of Saturn, and we expect a lot of impacts. Very lightweight impacts, more like going through smoke than particles. Every now and then we'll see a slightly higher impact, but still very small material. We believe that the ring, the D ring, which is the one that's slowly extending into Saturn, at the point where we're going through is diffuse enough that we should be fine. Nevertheless, you do that 22 times, and we have a probability of losing the spacecraft of slightly under 99%. I'm sorry, slightly over 1%. We have, let me make myself perfectly clear. We 98.8% chance of being successful. Our most conservative, most dire models, where all the engineers awfulize everything, put us at 97%. We would never take a flagship mission on that kind of course in any other time of the mission except when it's about to end. Once we've flown by Titan, T-126 is its nomenclature, it's really our 127th Titan flyby. In April, Cassini is essentially on a ballistic trajectory into Saturn. Because of those orbits that Joni showed you, Titan's still there, and we can't, even if we wanted to, can't avoid it enough to not have it put us into Saturn September 15th. So even if we do lose the spacecraft completely, the science is gone, but any issues of contaminating Titan or Enceladus are moot.
I think we had a question here.
Emily Lakdawala from the Planetary Society, and thank you for a wonderful mission. And my professional career began reporting on Cassini, so it's been quite a journey for me too. I have questions for Linda and for John. For Linda, I'm wondering if you can tell me what questions Cassini has raised that you couldn't possibly answer with Cassini, that you need to do something else in order to answer those questions.
Oh, there's a large number of questions that Cassini has raised, and I'll just highlight a couple of them. One has to do with the tiny moon Enceladus. We thought this tiny moon would be frozen solid and inactive, and what a surprise to find not only geysers of water vapor and water particles coming out, but to find organics, a salty global ocean underneath the icy crust, and even the possibility of hydrothermal vents, the conditions that could be right for life, to find an ocean world that small with conditions right for life. And then, of course, Titan's surface, seeing it for the first time, seeing the methane lakes and seas, understanding that clouds form with methane, it rains methane. To understand and see that surface was really a complete surprise. Voyager just saw a fuzzy ball, and it took the Huygens probe and Cassini to reveal that incredible world. And then each of the moons have gone from pinpoints of light, or in some cases some pretty good data, back from Voyager, to worlds in their own right. We have red streaks on Tethys. We have interesting fractures on Dione. We wonder if Dione, too, might have been active or be active at some level. So many questions. And then this water-filled magnetosphere, that wasn't expected because, of course, the source of the water is Enceladus itself. And then for the planet, there's still questions about the atmosphere. We haven't had a probe yet into Saturn's atmosphere, so a future mission might go deep into Saturn's atmosphere, as we did with the Galileo probe at Jupiter, to better understand it. So you've got the planet, Enceladus, Titan, many places to go back with another mission.
Did you want to chime in on that at all?
Yes, I did. So let me also mention that we have released an announcement of opportunity called New Frontiers that allows further exploration of Enceladus, but also Titan. Titan is a fabulous world, I think really surprised so many of us. Because as I mentioned, it's Earth-like in the sense that it has liquid on its surface. It has a cycle of methane, much like our water cycle. And it has plenty of organics, but it is so cold, and methane being the liquid brings up the question of a different potential life environment. So maybe Titan holds us in question about how we view life as being DNA-based. Perhaps it's based on a completely different system, and Titan might be able to give us that hint or that view into an environment that's so different but still could support fascinating types of life. We call that field of research weird life. And that's a gateway to what we might find for exoplanets. So indeed, there's plenty left to do.
Thanks a lot, Jim. We're going to go to the phones now. I think we have Bill Harwood on the line from CBS News. Bill, are you there? All right. I think we also have Tracy Watson from USA Today.
Oh, I'm here.
Oh, there's Bill. There's Bill. Go ahead, Bill.
Sorry about that. My daughter had just rung in.
I'd like to ask Earl about the details of the encounter. I'm curious how much fuel Cassini still has going into the final flyby. How much fuel, is any fuel needed after that? Or, give me a little bit of a look at any maneuvers that are planned. And during the crossings itself, I heard the velocity 76,000 miles or hour or kilometers per, I'm not sure which. They're both big numbers. What does that do with imaging? I mean, where are you doing imaging on these flybys, and what sorts of resolution can you achieve? Thanks.
Okay, Jim, I'm going to punt that first part of that question to Julie Webster. So while the microphone is coming up to Julie, I don't know exactly where it got. I'll tell you a little bit about that 76,000 miles per hour. It smears the dickens out of the images. So we really can't take images right up that close. We have to be a little further away. But to answer some of the prop questions, I'm going to put this on to the Spacecraft Operations Manager, Julie Webster.
Okay, I had the funny feeling that was looking up, so while you were doing the Eyes on the Solar System, I looked up Todd Barber's last prop report. We've got about 36 kilograms of hydrazine left. Those are the little thrusters. And that's about where we wanted to be to finish up, because we'll use a lot of hydrazine. We use hydrazine every day to keep the reaction wheels spun to the right place. And then we also use them, we'll use them for the Titan 126 flyby when we go by at 979 kilometers. So we'll use about 10 to 15 kilos of that 36 that's left. And I'm going to fudge Todd's numbers here a little bit, because this is the big question is the fuel, the bipropellants, the monomethyl hydrazine and the nitrogen tetroxide. There's about 10 plus or minus 20 kilos of the fuel left, and that's the one that we're worried about the most. And we could be out today, we could have 30 kilos. The oxidizer's a little bit more. The oxidizer's running about 25 plus or minus that same 20. And so there's no more main engine maneuvers planned. We may need one at the end, but there's no more main engine maneuvers planned. We are doing maneuvers prior to T126, 3 days before and 3 days after, and hopefully that'll be done on hydrazine.
Thanks, Julie. Appreciate it. We have another call from Tracy Watson at USA Today, I believe.
Yes, thanks. Can you hear me?
We can, thanks.
Okay, great. Can you talk about how close you'll come to the planet itself before you plunge into the atmosphere, how big the gap is between the D-ring and the planet, and how hard it is to target that gap? That would be great. Thanks.
Well, Tracy, the last 5 orbits, first of all, Saturn's atmosphere has been not an easy thing to nail down. It's been moving back and forth. We once thought we were going to actually be too close and have to fight with it. Then it's kind of moved back in, and we thought we'd have to dive back closer to get a sample. Now it's back in the middle of those two places. So relative to how close we're getting, we expect the final 5 orbits to actually be within the sensible atmosphere, and we'll be sampling of it. And of course, the 6th orbit will be way inside. The gap is about, 1,200 kilometers. I think you may hear, 1,200 miles. You'll hear 1,500 or something like that, but I hold project managers reserve on both ends of that in order to keep us out of trouble. So the gap's about 1,250 miles. The navigation of that is actually pretty straightforward. We have that system, the navigators, I should say, I'll use the royal we here, have that system so well calibrated, and the gravitational forces, the dynamics of the spacecraft and Saturn and its moons, that trajectory, if we don't fiddle around with it, is really pretty rock solid. The most concern so we may be a handful of kilometers off in altitude on each of those passages through the ring plane. A little bit more uncertain on when we're going to pass through. That might be on the order of a few tens to a few hundreds of kilometers, but that doesn't matter anywhere near as much for health and safety as it does where we are between the rings.
Let me add that the navigation system is absolutely incredible. We have flown within 25 miles or so of the surface of Enceladus, actually through the geysers, and it's just incredible. So, hey, 1,200 miles, that's nothing.
All right, let's go to social media now. Stephanie Smith from our social media team standing by. Steph, what do we have?
We've got a lot of outpouring of emotion, a lot of fans of Cassini online, many of who've come to know the mission through the photos that it's taken. And Misra on Twitter would like to know, in your opinion, what's the most stunning picture taken by Cassini so far?
Well, I think for me, one of my favorite pictures, and I think the most stunning, is the backlit Saturn. That picture where Saturn is covering up the sun, and you see the rings blazing in all of their glory. You see actually a ring of light around the planet as the sunlight refracts through the atmosphere, and it's just not only a stunning picture scientifically, but also very beautiful. And if you look carefully, you'll find the Earth, Mars, and Venus in that picture as well.
Well, she stole my answer. That's my favorite one too. It's the background on my laptop. So.
So both Artem on Facebook and Lars on Twitter are wondering about the detail of the imagery that we're going to see during the grand finale. So what scale are we talking about? What size ring particles could Cassini resolve?
When we're in very close, we could probably see ring particles on the order of a kilometer or so. A couple, or maybe a little bit bigger. And there'll probably be clumps of ring particles, but it's tricky because there's a lot of ring particles around it and a lot of scattered light. But the bigger ring particles tend to sort of shoulder the other particles out of the way, opening up a gap. We call it a propeller gap. So maybe we'll see a propeller parent or two in the grand finale orbits.
And one final one for this batch. At what distance above Saturn before the finale will we receive any last photos, and how long will it take for us to get them?
Well, actually, we're going to be getting our last photos a fairly great distance away. We basically several hours or 12 hours before, we're actually going to point the high-gain antenna at the Earth and just sit in that configuration, and that will be the end of sending any images. Other data will continue to come back, ion and neutral mass spectrometer, fields and particles. So you're looking at maybe half a day or more out, maybe even a day out for the last pictures. We are going to take a really beautiful mosaic of the planet and the rings in that final day of the mission.
And what's the one-way light time?
An hour and
About
80
90
minutes.
Yeah.
And Jim, I think you're going to be out here at JPL with us, excitedly waiting for those images as well, right?
Oh, absolutely. You couldn't tear me away. But I did want to make mention of what I think is my favorite image, and there are so many of them. It's really one where we had a fabulous view of Enceladus and a detailed look at the geysers. And what surprised me immediately is in the dark portion, we could see material coming up indicating that it's not just a geyser, but a literal wall of water leaving that body, flying into space. This means these cracks all along the entire length are very active, pouring liquid water and other elements that's in that ocean out for us to taste. This gives us a great feeling about potentially sampling those plumes with future mission. You know, Enceladus really was, to me, that first ocean world that got us thinking about a brand new paradigm of where bodies could be habitable for life well beyond our knowledge of our terrestrial planets. So it's just an exciting image every time I see it.
Thanks, Jim. Back here in the room, any other reporters with questions? Hands raised. In the back there. You can wait for the mic if you would.
Paul Verkammen, CNN. Based on the success of Cassini-Huygens, any missions that you never envisioned decades ago that you now think might be possible?
Oh, lots of possibilities there. Certainly a mission to Enceladus, perhaps to orbit, maybe even land and go into one of the cracks on Enceladus. A lake lander on Titan, to take a craft down and land in one of the lakes or seas and actually look for a possibility of life that we couldn't have even imagined. So those are just two.
All right. I think we have another call on the phone. I think we have Dave Mosher from Business Insider. Dave, are you there?
Yes, I'm here. Can you hear me?
We sure can.
Great. I have a main question and a follow-up question to that. So as I understand it, plutonium-238 and radioisotope power sources made this mission possible. Earl, first of all, I'd just love if you can speak to that a little bit and how that technology made this mission possible. As I also understand it, the Department of Energy is producing plutonium, and I've spoken with those people, but it seems like that program is a few years behind schedule. Jim, I was curious if that might hamper the announcement of opportunity you were talking about for the Titan Enceladus mission. Thanks.
Well, I'll let Jim answer the second part. As you appropriately pointed out, that's his. But yeah, the RTGs, the radioisotope thermal generators for Cassini, absolutely enabled the mission. We could not have carried the kind of attitude control system that would have been required if we had solar panels. We've often been quoted as saying that solar panels would be the size of football fields. That's probably not a little bit of a hyperbole, but it's not far off. And to try to do what we've done with this spacecraft, with all these fixed parts, it just would not have been conceivable. So they essentially enabled the mission. I know that Europa is going to use solar panels at Jupiter, and Juno is doing that right now, but at 10 AU, it's 100th the sun out there, and we just didn't have any other alternative. And frankly, the RTGs are still going strong. We have enough power for another decade at least, but we don't have the propellant. And Jim, for the second part's yours.
Okay. So indeed, we work with the Department of Energy, which manages the stockpile of radioisotopes for the country. And in that stockpile is a significant amount of plutonium, not only for our next mission, which will need plutonium-238, which is the Mars 2020 rover that will launch in 2020, land in 21, to core samples on Mars. But also, it's enough for us to be able, in our announcement of opportunity for the New Frontiers set, to be able to offer radioisotope power. Our work with Department of Energy is going extremely well. They're just a wonderful partner. And indeed, we've been approved by Congress and the administration to move forward with making additional plutonium. So that means between NASA and Department of Energy, we are really going to be good stewards of the planetary program, providing enough plutonium for these missions I mentioned, but many future missions to come.
Thanks, Jim. And I think we have a quick follow-up from Tracy Watson at USA Today. Go ahead, Tracy.
Yes, thanks. How long do you expect the spacecraft to last once it plunges into the atmosphere on the final rev? And what are you going to do to commemorate or toast your mission? Thanks.
I think the spacecraft is expected to survive kind of intact for about 3 minutes. And then it will be just disassociated very soon thereafter. That's the second question. I'm going to pass that one along.
Yeah. Well, I can imagine that we'll be gathered with our Cassini family here at JPL, waiting for that final moment. And I think once the signal is lost, that heartbeat of Cassini is gone. I think there'll be a tremendous cheer and applause for the completion of an absolutely incredible mission. Hugs, tears, the Kleenex box will get passed around, and we'll just sort of rejoice in being part of such a wonderful mission.
And there is a laboratory policy, but maybe we'll find something to toast with.
All right, with that, we'll take one more question from social media. Steph, if you've got one.
All right, this is about sort of the heritage and legacy of Cassini. Thomas Schumann on Twitter would like to know, what can we learn about building future space probes from the 20 years that Cassini has been in space?
Well, I think we can take advantage of new technologies and could build better instruments now. We can tailor the kinds of instruments for the science we'd like to collect. A good example is Enceladus. If you want to go back, fly through those plumes and collect free samples, you'd now know what kinds of mass spectrometers, what kinds of instruments that you'd want to carry. And just we can really build spacecraft. NASA does a great job, and they can last a long time. And so that's part of the excitement. There are other two worlds, Uranus and Neptune. We need to visit those. Maybe we need additional Cassini-like spacecraft to continue pushing out that frontier in our solar system.
And Jim, do you have anything to add to that? I imagine you would.
I do, indeed. Right now, we are planning a mission back to Jupiter. It's called the Europa Clipper, and it's one that's now going to interrogate Europa, which is a very large moon. It's about the size of our own moon that has hardly any craters on the surface. We believe from Hubble observations that it also has plume material where the ocean is communicating with the surface. This is just a tremendously exciting mission. But what we've done with that mission, because the radiation environment around Europa is so difficult, is we're really taking a page out of Cassini's book. And that is, we really understand globally a lot about Titan. Because of those multiple flybys, we understand the distribution of the methane lakes, its cloud structure. It's not just a one pass, but it's been multiple passes, just like an orbiter. And so for Europa, the Europa Clipper mission, we're going to orbit Jupiter, but make multiple flybys of Europa and get that global picture. So already we're learning so many things about Cassini that we could use on other missions, and there'll be more like that to follow.
I might just add just a brief moment. The Cassini, I believe, has also revalidated the concept of a flagship, a mission that is absolutely bristling with instruments. We're covering the entire spectrum from deep infrared to far ultraviolet. We have radar, we have fields and particles, in situ instrumentation, and some of Cassini's most surprising results have come from unexpected places. And that value of not knowing exactly what you're going to find, but being ready for anything, taking that technology to the next level, I think, is just absolutely critical. It's expensive, but the payoff is well worth it.
All right. Well, that's all the time we have. Thank you again to our speakers and to Dr. Green from Washington. Thanks to everyone who submitted questions. More information about Cassini's grand finale, including links to the graphics and videos we shared with you here, is available online. Go to saturn.jpl.nasa.gov/grand finale. Head over there and look under Mission Resources. We'll also post a link to an archived video of this briefing when it's available. Thanks so much for joining us.